back. We're dealing with molecules and thermal expansions, moving right along. Solids, liquids, and gases. That's what we're going to explore today. Matter is made up of tiny particles or atoms or molecules which are too small for us to see directly. Molecules consist of even smaller particles known as atoms. Atoms can be viewed under an electron microscope. The arrangement of atoms in solids, liquids, and gases are a little bit different. In solids, the atoms are very closely arranged. They're held together tightly by very strong bonds, and they're able to keep their shapes. In the liquids, the molecules have weaker bonds, and they're able to pass or glide past each other. Okay? They're not able to keep their shape. They conform to the shape of what a container is holding them. And with gases, they have very weak bonds in between the molecules, right? So they're able to spread around and float around easily, okay? They don't keep their shape unless they're kept within a sealed container. Now here's tabulated information on the three phases: solids, liquids, and gases. Here you see that solids have very strong intermolecular forces. They have high density, meaning that they're tightly compact. The shape is fixed, and the ability to flow, they have very rigid bonds. It does not flow very easily. They're not easily compressed, meaning they cannot be squashed easily. And the particles just vibrate when they're exposed to any type of heat that will cause the particles to move along or vibrate. Liquids, the particles again are very close together. The intramolecular forces are intermediate. The density is very high because the molecules are close together. The shape takes the shape of the container. These have weak forces between the particles, so they are able to flow. They're not easily compressed because the particles are close. Particles vibrate and translate, constantly changing neighbors. Oh yes, so constantly changing neighbors, meaning that I'm here with you and then I'm moving past you to go by another particle inside of the liquid or fluid. Gases, the particles are very, very, very far apart. They're weak. The intramolecular forces are weak. The density is very low. They take the shape of the container. If it is in a container or outside of a container, gases have no shape. These have very weak forces between the particles, so they are able to flow. Easy to compress because particles are far apart, meaning that they're easy to squeeze together, and the particles translate freely, having neighbors only at the time of collision. So here you have it, all the differences existing between the phases, different phases, and the differences are arrangement of particles, intramolecular forces, that's between the atoms, density, shape, ability to flow, compressibility, and main motion of particles. Intramolecular. There's also intermolecular, which are forces that exist between molecules, gaseous molecules. Now, the kinetic theory of particles says that the particles of matter, atoms, or molecules are always in constant motion of vibration, translation, or rotation. So vibration means to shake, translation means to move side to side, and rotation means to roll over, right? There's space between the particles. Forces or bonds pull them together when they are near to each other, and so the particles have potential energy. When a substance is heated, the heat energy supplied could result in an increase in the kinetic energy of the particles of the substance, and hence in its thermal energy, causing the temperature to rise. So thermal means heat, right? When a substance is heated so that it changes state, the heat energy supplied results in an increase in the spacing of the particle, and hence an increase in their potential energy, allowing them to break bonds with their neighbors and to expand against any surrounding pressure. So here we have a question, well, two questions. Describe solids, liquids, and gases in terms of the separation and motion of their particles and the forces between their particles. So if we're supposed to take solids by themselves, we say the separation and motion of their particles. Well, the atoms or molecules or particles, whatever you want to say, are very, very close together. They have strong intramolecular bonds. They don't move much. If heat is applied to them, they vibrate. Whereas with liquids, you have like slightly like less strong bonds. The particles are able to flow past each other. And then with gases, very, very weak bonds, and the particles just is very far apart, and so they pass all over the place. Okay, so the forces are very weak, and we call those forces Van der Waals forces. Explain the following properties of a liquid in terms of your description in question 1. So for solids, high density, shape, fixed, compressibility, can't be compressed much, fluidity, no. Liquids, density is high, the shape is when it conforms to whatever container it's in, compressibility low, and fluidity high. Density for gases low. The shape is dependent on the container it's in. The compressibility, easy to squeeze, fluidity high. Now we're moving on into thermal expansion. When heat is applied to certain substances, most times you will have expansion, especially in metals. And so we're going to investigate that today. When matter is heated, so metals and gases, we could think along that path right now. When matter is heated, it expands. When matter is cooled, it contracts. So expands, you can see I use the font that's nice and fat. They expand going across like that. And cooled, that means it's coming back together. Right? When a metal is heated, it expands. We could all attest to that. Like for instance, if I were to heat up my ring right now, and you know, if my finger didn't have any feelings, and I tried to put it back on my finger, my finger won't go in. Thermal expansion is a major cause for the buckling of railroads in places that experience extreme heat. Right? So as you can see this nice little picture here, there's buckling right here in this area and buckling right here in this area. That's due to expansion, heat expansion. So uses of thermal expansion. So people or companies use thermal expansion for their benefit. So here we have an example, shrink fitting. Axles can be shrunk by cooling them in liquid nitrogen at negative 196 degrees Celsius until the gear wheels can be slipped onto them. On regaining normal temperature, what do you think happens? Yes, on regaining normal temperature, the wheel will expand. Right? The wheel will expand, or the axle. I think the axle will expand because that's the one that was cooled. So the axle will expand. So this purple thingy is going to expand. Opening of tight lids. So here's another use of thermal expansion. Sometimes you have trouble opening lids off of mason jars, and you start to call people and say, you can help me, you can help me. Actually, you could run that lid underneath some hot water and you could cause the lid to expand, because the lid is usually metal, right? So once it's metal, it's going to work. You put it under some hot water. The only thing is that the lid is going to get hot, and you're going to have to, if you could withstand the heat off of that lid, then you could turn it, or you could use a mitten and then open it. So instead of exposing your bare hand to a hot metal lid, you could use a mitten and open it. So that's what happens when you add some hot water or you use a blow dryer to heat it up, I think the blow dryer would even make it hotter. It will cause the lid to expand and bump off of the ridges that's holding it, and then you'll be able to pop it off easily, right? Here's another use, bimetallic strip. So a bimetallic strip consists of two different types of metals that's riveted together. The strips bend on heating such that the metal that expands more is on the outer side of the curve. How do you determine the outer side of the curve, right? Weird. So let's just say, I guess whenever it's in some sort of contraption, you put the one that expands more on the outside, or wherever you want it to make a contact point. So bimetallic strips are used in fire alarms, and so heat from the fire causes the strip to bend upwards and close the contact. So bimetallic strips are actually incorporated into circuitry, and so once it's in that circuit, it would therefore complete the circuit when it is affected by heat or exposed to heat. So here's an example. Here's a bimetallic strip, and we have metal A and metal B, no names given, and we see here that when metal B, let's go with the expansion because it's easier to see this. When the metal, the riveted set of metals is heated up, the B expands more than A. The one on the outside, it stretches more than A. And then when it is cooled down, B contracts more than A. So it gets shorter quicker than A. You can see that there. Bimetallic strips are also used in the thermostats, in refrigerators, ovens, irons, and heaters. So that's a lot of uses for bimetallic strips. What is a thermostat? A thermostat is an electrical device used to control temperature. It bends when it gets hot to break the circuit. Here are some ways we can avoid problems due to expansion. So firstly, concrete cracks when heat is put upon it, or when it is exposed to heat, concrete cracks. Right? And if you just throw down a large bit of concrete, what happens is that the crack is going to just travel from point A to point B if there's nothing to stop it. So what people do, if they pave roads using concrete, you'd realize that the roads are laid in slabs. They're separated by joints, or sometimes even board. But I've seen the board. I don't see pitch a lot, but I see the board a lot. And so they separate them with some boards so that if a crack happens in this part of the concrete, guess what? It stays in this part of the concrete. And if a crack happens here, it stays in this part. However, if you have concrete that spreads without any joints in between, that crack will, if it cracked here, it will travel all the way across right to wherever the concrete ends. So it's like trying to protect the concrete from cracking too much. So that's one. And then we have railway lines that are laid in short lengths, and they are beveled to overlap each other. So when they expand, they just slide past each other. So this is the bevels right here, and you see the cuts right here. So when they expand, this would expand this way, and that would expand that way. So it wouldn't have any buckling. So beveled ends stop buckling. That's what it does. It stops buckling. Pipelines in deserts, are those which carry steam, are laid in zigzag formation with flexible joints to allow the pipe to expand easily when they start to expand or spread apart. So there is a flexibility allowed for the pipeline to expand once it gets too hot, or once it gets hot. Now, large structures such as bridges can be made with one end on rollers. This allows them to expand and contract with ease. Baking dishes are made of materials that expand and contract with very little temperature change, or due to very little temperature change. This prevents them from cracking when removed from the oven into the much cooler environment. And as you can see here, I put a Pyrex dish. We all should have Pyrex dishes in our homes, and if you realize that these things, once they go into the oven, which is very hot, and they're removed and put onto, let's say, a stove or some kind of grill to cool, they do not crack, and that's because of the material they're made from. Now here's a good question. Wires. Why are telephone wires left to sag? Correct. Now this applies to mostly very cold countries, and maybe a little bit to here, to little islands in the north that experience a lot of chilly breeze in the December time, somewhere between November, December, January, February, around those 4 months where it gets very chilly. You would say that they're left to sag because when you experience colder weather, the metal that the wires are made of are going to contract. And if they're not left to sag and they contract, they can burst. And then if they burst, what's going to happen? It's going to be a hazard, because if that bursts and somebody is right there and the wire not only licks them and probably bursts it back open, it's going to electrocute that person, because you have electricity running through that wire all the time. Now, cracking of glass vessels. What happens when hot water is poured into a thick glass, and why? Exactly. When hot water is poured into a very thick glass, the glass is not given time to heat up uniformly, and because of that, there's sudden vibration happening at the bottom of the glass that's not happening at the top of the glass. And so that vibration is happening, and everybody's going crazy down there. All the atoms going crazy, and so eventually they crack, because down at the bottom is not what's happening at the top. Okay, and so that causes fissures and cracks in the glass. So due to heat not heating up the glass uniformly and a difference in temperatures between the two, cracking occurs. The unusual expansion of water. As water is cooled to 4 degrees Celsius, it contracts, as expected. However, between 4 degrees Celsius and 0 degrees Celsius, it expands surprisingly. Water, therefore, has a maximum density at 4 degrees Celsius, meaning that water is at its heaviest, right? Water is at its heaviest at 4 degrees Celsius. Now, the funny part is that most liquids, when they are frozen, they are heavier. They're frozen, meaning when they're frozen into solid phase, right? They are heavier than their liquid counterparts. However, with water, when you freeze water and put it back into itself as a liquid, ice floats, right? Weird. It floats because of the packing. Okay? The packing of the molecules, the packing of water molecules in liquid water is very closer, is much closer than when it's packed in ice. In liquid, as you can see in the picture, you will notice that all the water molecules are very close and they could glide past each other, and they constantly break and reform hydrogen bonds. However, with ice, the packing of the water molecules is a bit different in that they're further apart and there are spaces, like little spaces in between there, in between all of this. And so ice becomes less dense. The packing of the molecules makes it less dense. Pretty much you can relate it to a ship. Ship is mostly made of steel, but guess what? That ship can float because there are spaces. There's a big air pocket called the hull. Ice inside there in the hull, allowing the ship to float, right? However, if you take that same ship and you were to crumple it up into a ball, that ship, that which was once a ship, is going to sink into the ocean, right? So it's all about the orientation. So if you were to answer a question, oh, why is ice less dense than water, you could speak about the orientation of the water molecules, in that they are less densely packed than in water, right? So water molecules in ice are less densely packed than in water, and also you have these air spaces in between, which lends to its lower density than water itself. And so I'm going to read this. At 0 degrees Celsius, when water freezes, a considerable expansion occurs, and every 100 cubic centimeters of water becomes 109 cubic centimeters of water. This accounts for the bursting of water pipes in countries where very cold winters are experienced. Remember the polar vortex? Remember that? I think that was last year. No, that was the year before last year. And they had all those pictures with people and the toilets that were cracking. Like the water in the water tank in the toilet rose and the tank cracked. That's crazy. That's crazy. So here again we have a beautiful picture, and we show you that ice has a formation, and the orientation of the water molecules are further apart. And then in warm water we have some expansion going on. The molecules are able to pass past each other. And then we have cold water, where cold water is much denser than warm water, because remember, the warmer something is, the more it expands, right? So yeah, so here you have it. I think, yes. So now we're going to deal with expansion of gases. When air is heated, it expands, and when it is cooled, it contracts. Okay, same thing here. So we have the expansion of the water molecules when it's warm, and then we have the contraction here. Contraction means to come back together. Contraction of when the water molecules are cold. And remember, the maximum density is at 4 degrees Celsius. So down here probably is about 4 degrees Celsius. Alright? And gases expand much more than liquids, and liquids expand much more than solids. Okay? So maybe we could do these questions. I got these out of a textbook. A really book right here. A very good textbook. So let's go. It says, explain why the metal lid on a glass jam jar, can be unscrewed easily if the jar is inverted for a few seconds with the lid in very hot water. You are definitely correct, because the metal lid would expand. Furniture may creak at night after a warm day. What's happening? Right, the furniture is now contracting. So in the hot day, the furniture was expanding, or had expanded, and now the night is cooler. You would see that, you would hear the noises as they contract. That happens a lot, not with furniture though, with the roofs. The roofs with the galvanized on it, you could hear them moving at night. You hear. Now, concrete roads are laid in sections with pitch between them. Right, that's to decrease the cracking that may happen in the concrete. So to decrease the spread of cracks. So you want to contain the cracks. So if you were supposed to remove the concrete slab or fill it, you'll be able to fill just that one. So it saves on the aesthetics of the road, and it also saves money, because if a crack goes from, it's like split ends, you know. You kind of want to stop the split end before it reaches to the, you know, it's like a ream. Let's talk about stockings here. So split ends and stockings. If you have a ream, you kind of want to stop the ream from happening by putting a polish rim around that ream. Or with split ends, you cut off the split end before it damages the rest of your hair. The same thing with concrete roads. You want to stop the crack before it affects the rest concrete slabs. Alright, so back to the questions. Let's do this question here. Explain why A, the metal lid on a glass jam jar can be unscrewed easily if the jar is inverted for a few seconds with the lid in very hot water. Well, you guessed it. The jar, because the lid is metal, it's able to expand, and therefore it's easier to remove from the jar. Furniture may creak at night after a warm day. Well, during the warm day, the furniture might have expanded, must have expanded, not might, would have expanded. And at night, nights are usually cooler than daytime, and so at nighttime now, you have contraction happening. There's contraction of the furniture, so you would hear that. Concrete roads are laid in sections with pitch between them. Well, it's like stopping split ends and stopping reams, right? You don't want a continuous crack running along the road, so you want the aesthetics to be maintained, the beauty of the road, and you also want to save money. If you stop a crack in its tracks, then you wouldn't have to fill a million different concrete slabs, or you wouldn't have to fill the entire road. The crack would just happen in that concrete slab, right? The same thing, like I was going to say with split ends. To stop the split end, you cut it off, right? You cut it off so it doesn't go all the way up. Same thing with ream stockings. You put polish on that ream so you could stop it from spreading. A bimetallic strip is made from aluminum and copper. When heated, it bends in the direction shown, and the one that bends more is aluminum. The one on the outer part right here. It bends more. Which metal expands more for the same rise in temperature? That's the aluminum. Draw a diagram to show how the bimetallic strip would appear if it were cooled to room temperature or below room temperature. Well, it's going to flip the other way. It's going to flip the other way, right? Because it's going to contract more. The aluminum is going to contract more. How does the bimetallic thermometer in figure 24.11 works? They have iron and copper, and they put it like this for a reason. So this is pushing this way. Yeah, because I'm just going to eat up these teeth so they don't move that way. And then this would therefore be bending this way. Yeah. And this will bend that way. Right? So and so this would bend like that, and this will bend over it, so the copper would expand more, causing this to go to the hotter side. Correct. Alright, so copper will expand more. Naturally, copper heats up or expands more than iron. Okay? So that's that, folks, for this lovely lesson on thermal expansion and molecules. That's it, folks, for this lovely lesson on thermal expansion and molecules. I hope you enjoyed. See you around.